An important application of acid-base equilibria that have a common ion effect is buffer solutions. And so let's spend some time learning a little bit about those. Our learning goals for this video would be to define the characteristics of buffer solutions and to learn a little bit about how they can regulate the pH. I want to start by introducing the Henderson-Hasselbalch equation. Now, we're already familiar with the weak acid constant, Ka, and it's given by the concentration of hydronium ion times the concentration of A- divided by the concentration of the undissociated weak acid. Now, we can make some very simple mathematical manipulations of this equation to get another more useful form. For example, we can take the logarithm of both sides, we can multiply through by -1, and then if we rearrange the equation a little bit, we end up deriving an equation for pH in terms of the pKa of the weak acid. Now, it's given by pH is equal to pKa plus the log of the ratio of the concentration of the conjugate base A- to the weak acid. This is something that's known as the Henderson-Hasselbalch equation. I want to note something special about this. It says that when those two concentrations are equal, when the weak acid and its conjugate base are both present in equal amounts, then the ratio is going to be equal to 1. So the log of 1 is 0, so that means the pH is just going to equal the pKa. So it gives us a really simple, direct way of determining pH for a solution in which you have those both present. Now you may be wondering, how do you get to arrange the ratio of those concentrations? Isn't it just what you get from an equilibrium situation? Under normal circumstances that would be true, but let's suppose that you mixed a weak acid and you're able to create a compound, say a sodium compound with the conjugate base as its anion, and when that dissolved in water it would split into ions, and so you would basically be seeding the solution with the conjugate base. So that way you can adjust both of those to have some desired concentration. Well, this is exactly what happens when you create a buffer solution. So a buffer solution is essentially a solution that has roughly comparable concentrations of both the weak acid and its conjugate base, and it's resistant to change in pH. So let's see how this works. Let's suppose we create an acetic acid buffer. Now, acetic acid has a Ka value of 1.8 times 10 to the minus 5. And let's say we arrange it in such a way that we're creating acetic acid and acetate ion, both in a concentration of about 0.20 molar. So from the Henderson-Hasselbalch equation, we would quickly find that the pH is just equal to the pKa of the acetic acid, and the negative log of 1.8 times 10 to the minus 5 gives us 4.74. So in general, when we create a solution like this, to find the pH, we would first find the pKa of whatever weak acid we happen to be using. We would compute the ratio of the two concentrations of the conjugate base to the weak acid. And then we would take the logarithm of that and add it to pKa. And when we finish with that, we would have the pH. So let's see how we might design a buffer solution with a particular desired pH. So let's say that our task is to create a buffer solution that has a pH of 4.5. Now the art of doing this, or I should say the reason for doing this, is that there may be some reason, other chemical reason in a solution that we want to have a certain pH at 4.5. So we would introduce a buffer to that solution so that it would try to maintain that pH so that it wouldn't destroy or disrupt some other chemical process that we want to take place. This is actually what happens in our blood. There are elements that maintain a certain pH in our blood. So the general steps that we're going to follow is we've got the desired pH of our buffer. We want to find a weak acid that has a pKa very close to that, because the whole idea is we want the ratio of the conjugate base to the weak acid to be as close to 1 as we can get it. So what might we do? Here are 3 possible weak acids that all have a pKa pretty close to the desired pH of our buffer solution. Now, we want this so that it makes those two concentrations be as close to equal as possible, and in order to achieve that, we want to get the weak acid whose pKa is closest to 4.5. Well, of the 3 that I've listed there, the acetic acid in the middle is the one that's closest to the desired pH. So then we would plug that into the Henderson-Hasselbalch equation. All right, and again, the pKa of acetic acid is 4.74, and we can use this now to solve for the ratio of those concentrations, and that will then instruct us how to create a solution that has that particular ratio. In this case, we would find that the ratio of those concentrations is 0.575, so that would be our guide for creating the buffer solution. Now, I want to close by talking about what happens in buffer solutions when we add things to them. So let's suppose that we've created this buffer solution, and we've done it with equal amounts of acetic acid and acetate ion, and we add 0.01 moles of nitric acid to this solution. Now, 0.01 molar nitric acid would normally have a pH of 2, so it's pretty acidic. The acetic acid, remember, has a pKa of 4.74. So what does the Henderson-Hasselbalch equation tell us? Well, this is the Henderson-Hasselbalch equation, but now what we need to do is plug in the values here. Now, I'll mention that both HA and A- are present in 0.2 molar. If I add 0.01 moles of HNO3 in a 1 liter solution, it's going to reduce the amount of A- by 0.01, and it's going to add to the amount of HA by 0.01. So in effect, what's going to happen is we'll see the pKa for acetic acid, 4.74, but now the logarithm of that ratio is going to turn, instead of being 0.2 over 0.2, it's going to be 0.19 divided by 0.21. And we find that the result here is a new pH at 4.70. So it's actually been reduced a little bit from 4.74. Now, a note that I want to make about this is that if you decrease that ratio of those concentrations, you're going to decrease the pH. If you increase that ratio, you're going to increase the pH. So in other words, decreasing that ratio is making it more acidic. Increasing that ratio is making it more basic. And that sort of follows, if you read that ratio right, the top is the conjugate base and the bottom is the weak acid. So if we're decreasing it, we're increasing the weak acid, so we're decreasing the pH, we're making it more acidic. If we increase that ratio, we're increasing conjugate base, so we're increasing that ratio, and pH is increasing and making it more basic. So here's a few thoughts about buffer solutions. They resist change to pH. They generally contain roughly equal amounts of weak acid and conjugate base. They can be tuned to a specific pH if desired. But I should mention, and something we haven't talked about but is mentioned in the lesson, is they have a finite capacity. You can't just keep endlessly adding acid to a buffer solution and expect it to maintain the pH. At some point you will have added enough acid that it's overcome the buffer and it will no longer control the pH. I mentioned earlier that blood is a buffer. It's very important because it maintains our blood pH between roughly 7.35 and 7.45. So it's a very fine-tuned control that keeps our acid balance in our bodies.